On the night of October 28th to 29th, 2025, the southern hemisphere of Earth fell into an unusual silence. Above the Atacama Plateau in Chile, where the air is so dry and transparent that the stars seem closer than the cities below, the Atlas telescope system continued its endless dance across the celestial sphere. Every few seconds, wide-angle cameras captured sections of the sky, comparing new images with previous ones, searching for what moves, what changes, what shouldn't be where it appeared. It was at this very moment, while most of humanity slept or went about their daily routines, that a small object in the solar system reached its closest point to the sun, perihelion, the moment of maximum approach to our star, when a cosmic body accelerates to its highest speeds, obeying the laws of celestial mechanics discovered by Johannes Kepler back in the early 17th century. Write in the comments where you're watching this video from and how much time you have to dive into this story today. It's important for us to know who's following this developing event along with us. The object in question received the designation 3I Atlas, the third interstellar object officially registered by humanity. The first was Oumuamua, which raced through the inner solar system in 2017, leaving behind more questions than answers. The second was Comet Borisov, discovered in 2019 by Crimean amateur astronomer Gennady Borisov. It behaved like a regular comet, vaporizing ice and gases as it approached the sun, which reassured the scientific community. But 3I Atlas, discovered on July 1st, 2025 by the same Chilean telescope that gave it its name, was different from the start. Its elongated shape, stretched in proportions rarely seen in natural comets, and the characteristic green coma of gas surrounding the nucleus made it special even among interstellar visitors. Professor Avi Loeb, an astrophysicist from Harvard University, who's been known for years for his bold hypotheses about the possibility of extraterrestrial technology, turned his attention to 3I Atlas almost immediately after its discovery. Loeb, who heads the Galileo Project searching for evidence of extraterrestrial intelligence, became one of the most controversial scientists of our time after suggesting in 2018 that Oumuamua might be an artificial object, possibly a solar sail of alien origin. His colleagues in the scientific community met this idea with skepticism, but Loeb kept insisting, absence of evidence is not evidence of absence, and science must remain open to even the most incredible possibilities if the data hints at them. On October 29th, the day of 3I Atlas's perihelion, Loeb published an essay on Medium titled "The Acid Test of 3I Atlas at Perihelion." In this text, he laid out a thought experiment that made many people think and others smile. Loeb suggested that if 3I Atlas is not a natural comet, but an artificial object, a kind of mothership from an alien civilization, then perihelion would be the perfect moment to execute its mission. At this point in the orbit, the object moves at maximum speed relative to the sun, and any smaller probes released from it would gain a significant speed advantage, like a stone thrown from a moving car flies faster than if thrown from a standstill. Loeb posed a question that sounded both poetic and provocative. Will 3I Atlas send mini probes to Earth as Christmas gifts to humanity? The professor's logic was built on precise trajectory calculations. 3I Atlas was scheduled to pass close to several planets in the solar system. On November 3rd, 2025, it would be at a distance of 0.65 astronomical units from Venus, about 97 million kilometers. On December 19th of the same year, the distance to Earth would be 1.8 astronomical units, around 270 million kilometers. And on March 16, 2026, it would approach Jupiter to within 0.36 astronomical units, about 54 million kilometers. These close approaches looked almost like a planned tour of the most interesting objects in the inner solar system. coincidence? Or something more? The ballistic calculations that Loeb presented in his essay were based on fundamental principles of orbital mechanics. If a hypothetical probe about 10 meters in size were separated from the main body at the moment of perihelion with relatively small initial velocity, say a few hundred meters per second, its trajectory could differ significantly from that of the parent object. Just as spacecraft use gravitational maneuvers around planets to change their course, a small object separated at the right moment and with the right vector could reach a given target using the gravity of the Sun and planets. In Earth's case, if such a probe were released on October 29th, it could reach the vicinity of our planet in about 7 weeks, by mid-December, about a week before Christmas, just as Loeb suggested. Why is perihelion the ideal point for such a maneuver? The fact is that at this moment, the object possesses maximum kinetic energy relative to the Sun. Kepler's first law states that planets and comets move in elliptical orbits, and the second law specifies that the radius vector connecting the Sun and the celestial body sweeps out equal areas in equal time intervals. This means that the closer an object is to the Sun, the faster it moves. At perihelion, speed is at its maximum. If at this moment a smaller object separates from the main body, it inherits this speed plus gains additional momentum from the separation mechanism. This allows it to move along a trajectory that would be impossible if separated at any other point in the orbit. Space agency engineers use similar principles when planning interplanetary missions, choosing launch windows when planets are in optimal positions relative to each other. It's important to understand that Loeb didn't claim 3I Atlas actually is an artificial object. He called his hypothesis a thought experiment, an intellectual exercise, a way to test our assumptions and readiness for the unexpected. In the scientific method, there's a concept of falsifiability, introduced by philosopher Karl Popper in the mid-20th century. A good scientific hypothesis must be one that can be disproven by observations. Loeb proposed exactly such a hypothesis. If 3I Atlas releases probes, we'll detect them. If it doesn't, the hypothesis will be disproven. Simplicity bordering on genius. But he also emphasized that the absence of probes wouldn't prove the object isn't artificial. Perhaps, if this truly is extraterrestrial technology, its creators simply aren't interested in contact at this stage, or use methods we're not yet capable of detecting. Earth's planetary defense systems, created to detect potentially hazardous asteroids, operate around the clock. Atlas telescopes, Pan-STARRS, Catalina Sky Survey, and other observatories scan the sky, tracking thousands of objects. They're capable of detecting objects ranging from a few meters to hundreds of kilometers, determining their orbits with high precision and predicting their movement years in advance. If any objects larger than a meter had separated from 3I Atlas, they would have been noticed within days or weeks. Modern image processing technologies allow for automatic detection of moving objects against the background of fixed stars, and any anomaly immediately draws astronomers' attention. By the end of October 2025, no signs of object separation from 3I Atlas had been detected, but the history of space discoveries is full of surprises. In 1986, the Giotto spacecraft flew through the coma of Halley's Comet and discovered that its nucleus was much darker than expected, almost black, reflecting only 4% of the sunlight hitting it. In 2014, the Rosetta probe reached Comet Churyumov-Gerasimenko and found that its shape resembled a rubber duck, two merged nuclei, which didn't fit at all with previous models of comet formation. Each new study of cosmic objects brings surprises, reminding us that the universe is much stranger and more diverse than we can imagine while sitting on the surface of our small planet. The green coma of 3I Atlas, its unusual shape, its interstellar origin, All of this makes the object worthy of close attention, regardless of whether it turns out to be natural or artificial. The color of the coma is usually associated with the presence of diatomic carbon, a molecule that fluoresces in the green range of the spectrum under the influence of sunlight. This same molecule gives the characteristic color to many comets approaching the sun, but the intensity and stability of 3I Atlas's green glow proved somewhat unusual, which raised additional questions about the chemical composition of the object and the conditions under which it formed in another star system before beginning its journey through interstellar space. As 3I Atlas continued its movement away from the sun after perihelion, gradually slowing under the effect of gravity, astronomers around the world pointed their telescopes at it. Spectrographs analyzed the composition of gases in the coma. Photometers measured changes in brightness that could indicate object rotation or material ejections from its surface. Radio telescopes attempted to detect any unusual radio signals, though with the understanding that natural comets emit nothing in the radio range except noise. Each observation added new details to the portrait of the mysterious visitor, but fundamental questions remained open. Where exactly did it come from? How much time did it spend in interstellar space? And the most intriguing question that worried not only scientists, but millions of people following the news: what will happen next? Avi Loeb in his interviews often repeated that science must follow the data, wherever it leads, even if it leads to uncomfortable or unpopular conclusions. He reminded us that when Galileo Galilei, in the early 17th century, claimed that Earth revolves around the sun and not vice versa, his ideas seemed absurd to most of his contemporaries and even led to conflict with the Church. When in the late 19th century scientists suggested that continents move across the surface of the planet, the theory of continental drift was rejected as fantasy, and it took several decades for it to be accepted. The history of science is a history of overcoming skepticism, expanding the boundaries of the possible, being willing to consider even the most incredible hypotheses if they're supported by observations and logic. Christmas 2025 was approaching. According to calculations, if hypothetical probes had been released on October 29th, they should reach Earth's vicinity around December 17th or 18th, a week before the holiday. Near-Earth space monitoring systems were operating in normal mode, tracking thousands of known objects and continuing the search for new ones. No anomalies had been registered. The sky remained the same as it had been throughout millennia of human history, full of stars, planets, and cosmic wanderers that obey the eternal laws of gravity and motion. And there was a certain beauty in this, a calmness, a reminder that the universe exists by its own rules, regardless of our expectations or fears. The Galileo Project, which Avi Loeb launched in 2021, was born from disappointment and hope simultaneously. Disappointment in how the scientific community reacted to Oumuamua, the first interstellar object discovered on October 18, 2017, by the Pan-STARRS telescope in Hawaii. The name Oumuamua in Hawaiian means messenger from afar arriving first, and this name proved prophetic. The object raced through the solar system at 26 kilometers per second, too fast for any object gravitationally bound to the sun. Its trajectory was hyperbolic, meaning it came from interstellar space and would return there, making only a brief visit to our star. But what really puzzled scientists was the anomalous acceleration that Oumuamua demonstrated as it moved away from the sun. Comets usually show non-gravitational acceleration due to the reactive effect of evaporating gases, which act like tiny engines, gently pushing the nucleus. But Oumuamua showed no signs of such activity, no coma, no tail, nothing that would indicate material ejection. Nevertheless, it was accelerating. Loeb proposed an explanation that made many of his colleagues raise their eyebrows. Perhaps Oumuamua was a solar sail, a thin artificial structure that accelerated under pressure from sunlight. Such sails had long been discussed in science fiction and in serious engineering projects as a way to travel between stars. If the object's thickness was less than a millimeter, with its length of about 100 meters, light pressure could create the observed acceleration. It was a bold idea, and the scientific community reacted predictably, with skepticism bordering on mockery. Most astronomers preferred more conservative explanations. Perhaps Oumuamua consisted of frozen hydrogen that evaporated in a way invisible to telescopes. Or it was a fragment of a planet destroyed by tidal forces when passing too close to its home star. Or its shape created unusual optical effects that we misinterpreted. Each of these explanations required certain stretches, but they seemed less extraordinary than the hypothesis of artificial origin. Loeb didn't give up, publishing papers and books defending his viewpoint. His book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, published in 2021, became a bestseller and simultaneously made him an outcast in the eyes of part of the scientific establishment. It was precisely this atmosphere of controversy that served as a catalyst for creating the Galileo Project. Loeb assembled a team of several dozen scientists, engineers, and enthusiasts united by a common goal: systematically search for signs of extraterrestrial technology using the scientific method, but without the a priori skepticism that often stifles innovative ideas. The project received private funding, which freed it from the need to go through traditional scientific grant channels, where such research is rarely approved. The team began developing instruments for detecting and analyzing anomalous objects in near-Earth space, as well as for studying already known mysterious phenomena that might have technological origins. One of Galileo's first projects was an expedition to search for fragments of meteorite IM-1, which fell into the Pacific Ocean near Papua New Guinea in 2014. Data analysis showed that this meteorite had interstellar origin and entered the atmosphere at anomalously high speed. Loeb organized a marine expedition that in 2023 lifted spherical particles of unusual composition from the ocean floor. Whether they were fragments of an interstellar object or simply rare minerals of terrestrial origin, debates continue to this day. But the very fact that a scientist with such a reputation personally led an expedition on a ship showed his seriousness and willingness to risk not only his reputation, but also time and effort to test his hypotheses. When 3I Atlas was discovered on July 1, 2025, the Galileo Project team immediately added it to their priority observation list. Initial spectroscopic data showed the presence of molecules typical for comets: water, carbon dioxide, cyanogen, diatomic carbon, which created the characteristic green coma. Nothing unusual at first glance, but when astrometric measurements allowed precise orbit calculation, it became clear that this was the third interstellar visitor, and its trajectory would take it fairly close to several inner solar system planets. This was an opportunity that couldn't be missed. If there's even the slightest probability that the object could be something more than just an ice chunk flying through the void, it must be observed with maximum attention. Astronomical history knows many cases where objects were first taken for one thing, then turned out to be something completely different. In 1781, William Herschel discovered an object moving among the stars and initially took it for a comet. Only subsequent observations showed it was a planet, Uranus, the first planet discovered in historical times. In 1801, Giuseppe Piazzi discovered Ceres, which was also initially considered a planet, then reclassified as an asteroid. and in the early 21st century given dwarf planet status. The nature of celestial objects isn't always obvious at first glance, and it takes time, observations, analysis to understand what exactly we're dealing with. The problem with identifying artificial objects in space is that we don't have reliable criteria for recognizing them. On Earth, we easily distinguish artificial from natural because we know what human creations look like and what nature's creations look like. But extraterrestrial civilization technology might be so different from ours that we simply wouldn't recognize it, even if it were right in front of us. Imagine showing a mobile phone to a person from the Middle Ages. They might take it for a strange stone or amulet, having no context to understand that it's a communication device. Similarly, we might look at extraterrestrial technology and classify it as an unusual comet or asteroid because we lack the experience to recognize its true nature. Loeb, in his works, often references a famous quote by Arthur Clarke, the writer and futurist who formulated 3 laws of predicting the future. Clarke's third law states, "Any sufficiently advanced technology is indistinguishable from magic." This can be rephrased for space objects. Any sufficiently advanced extraterrestrial technology may be indistinguishable from a natural phenomenon, especially if we don't know what exactly to look for. This doesn't mean every unusual comet is a spaceship, but it means we should be open to the possibility and carefully search for signs that might indicate artificial origin. What signs could indicate that an object is artificial? Loeb identified several criteria. First, anomalous orbital characteristics, such as acceleration without visible causes, like Oumuamua. Second, unusual shape or size ratios, greatly different from what we see in natural comets and asteroids. Third, regular brightness changes or other patterns that might indicate mechanisms at work. Fourth, unusual chemical composition or temperature characteristics. Fifth, and most direct, detection of radio signals or other forms of radiation that cannot be explained by natural processes. And finally, the most obvious, separation of smaller objects that move along trajectories different from the main body, especially if these trajectories are directed toward interesting targets, such as planets with atmospheres. It was precisely this last point that formed the basis for the mini probes by Christmas prediction. The logic was simple. If 3I Atlas truly is a mothership, then perihelion is the perfect moment to release research probes. They would get maximum momentum from the parent object's speed and could reach interesting targets in a short time. The size of such probes could vary from several meters to tens of meters, small enough to be effective, but large enough to carry necessary instruments. Modern detection technologies are capable of spotting objects as small as 1 meter at distances of several million kilometers. So if probes exist and are larger than a few meters, monitoring systems would definitely detect them. By the end of October 2025, observations of 3I Atlas continued at observatories on all continents. The southern hemisphere had an advantage during this period since the object was in the southern part of the sky, but large telescopes in Chile, Australia, and South Africa provided a constant stream of data. Spectrographs at the Very Large Telescope in Chile, one of humanity's most powerful instruments, analyzed light reflected from the object and emitted by its coma. Each spectral line told a story about chemical elements and molecules present in the object. Water, carbon, nitrogen, oxygen, all the building blocks of life as we know it, but in forms and proportions that formed around another star, under conditions we can only imagine. Interstellar space isn't absolute vacuum, but it's close. The density of matter there is about 1 atom per cubic centimeter, many orders of magnitude less than the best vacuum we can create in a laboratory. Temperature is about 3 Kelvin, just 3 degrees above absolute zero, thanks to the cosmic microwave background radiation that permeates the entire universe. An object traveling through such space gradually cools to this temperature, becoming colder than imaginable. Cosmic rays, high-energy particles, bombard its surface for thousands or millions of years, slowly changing the chemical composition of outer layers. When such an object enters the solar system and begins warming from sunlight, frozen gases start to sublimate, transitioning directly from solid to gas, creating the coma and tail. 3I Atlas demonstrated all these signs of an ordinary comet, which reassured most astronomers. But Loeb and his team continued asking questions. Why is the elongated shape so stretched? Why does the intensity of green glow remain so stable, while in most comets, it changes as distance to the sun changes? Why is no rotation observed, or is it so slow that it doesn't lead to noticeable brightness changes? Each of these questions had potential natural explanations, but the combination of unusual characteristics made one think. Science progresses not only thanks to answers, but also thanks to properly asked questions. In the history of searching for extraterrestrial intelligence, there were several moments when scientists thought they had detected a signal or artifact. In 1967, astronomer Jocelyn Bell discovered regular radio pulsations so precise that the source was initially called LGM-1, where LGM stood for Little Green Men. It later turned out to be a pulsar, a rotating neutron star, a natural object, but at the time of discovery, the possibility of artificial origin was seriously discussed. In 2017, Tabby's star, KIC 8462852, showed strange brightness variations that didn't fit any known model. Some suggested that a Dyson sphere was being built around the star, a megastructure for collecting stellar energy. Subsequent research showed that brightness changes were most likely caused by dust clouds, but for several months, this star became one of the most discussed topics in astronomy. Such false alarms shouldn't discourage the search, Loeb believed. On the contrary, they show that the scientific community is capable of seriously considering extraordinary hypotheses, testing them, and reaching reasoned conclusions. Problems arise when skepticism becomes dogma, when certain ideas are rejected not based on data, but on prejudices. Carl Sagan, one of the most influential science popularizers of the 20th century, formulated a principle that became a catchphrase. Extraordinary claims require extraordinary evidence. Loeb fully agreed with this principle, but added an important clarification. To get extraordinary evidence, you need to look for it, not dismiss the possibility in advance. November 3rd was approaching, when 3I Atlas was supposed to pass its closest point to Venus. This was the first test for the probe hypothesis. If they would be released, and if one of them headed toward Venus, its trajectory would start differing from the main object's trajectory within the first days after separation. Tracking systems were ready. The world, largely unaware of Loeb's prediction or considering it another piece of science fiction, continued spinning. But those who followed the developing events knew that the coming weeks could either be another confirmation that we're alone in the cosmos, or the moment that changes everything. On November 3rd, 2025, 3I Atlas reached its closest point to Venus, the second planet from the Sun, a world the ancient Romans named after the goddess of beauty, but which is actually hell, with surface temperatures around 470 degrees Celsius and atmospheric pressure 90 times that of Earth. The distance between the object and the planet was 0.65 astronomical units, approximately 97 million kilometers. By cosmic standards, this is close, though not close enough for Venus's gravity to significantly alter the comet's trajectory. But for observers following the development of Loeb's hypothesis, this was a moment of truth. If any probes had been released to study the planets, one of them might have headed precisely toward Venus. Venus has always held a special place in the history of searching for life beyond Earth. In the first half of the 20th century, before radars and spacecraft penetrated its dense clouds, many scientists and writers imagined it as a tropical world, possibly covered with oceans or jungles. When in 1962, the Soviet probe Venera 3 reached the planet and transmitted the first data about its true conditions, illusions were dispelled. Subsequent missions, including the Venera series that continued until 1984, and the American Pioneer Venus and Magellan, revealed a world of volcanoes, sulfur clouds, and a surface hot enough to melt lead. But in recent years, interest in Venus rose again after the discovery in 2020 of signs of phosphine in its atmosphere, a gas that on Earth is associated with biological processes. For a hypothetical alien civilization studying the solar system, Venus would present scientific interest as an example of a planet where the greenhouse effect spiraled out of control. Billions of years ago, Venus possibly had oceans similar to Earth's, but gradual heating led to water evaporation, carbon dioxide accumulation in the atmosphere, and irreversible climate transformation. Studying such a planet could provide important lessons about how planets evolve and what can happen if balance is disrupted. From an astrobiology perspective, the upper layers of Venus's atmosphere, at an altitude of about 50 kilometers, where temperature and pressure are more moderate, are considered a possible niche for microbial life floating in sulfur clouds. Atlas telescopes and other observatories scanned the area around 3I Atlas's trajectory in the days before and after the Venusian flyby. Automated image processing algorithms compared shots taken at intervals of several hours, searching for any new objects that might have appeared and started moving along a different trajectory. This was routine work that planetary defense systems perform constantly, but in this case, it drew special attention from a small group of enthusiasts following the developing events. Each data update, each new image was analyzed with hope and simultaneously with healthy skepticism. By the end of the day, on November 3rd, the results were unambiguous. No new objects had been detected. 3I Atlas continued moving as a single entity, with no signs of fragmentation or separation of smaller bodies. This result was expected by most astronomers, but it didn't close the question completely. First, probes could be too small for detection at such distances. Objects smaller than a meter are virtually impossible to spot at distances of tens of millions of kilometers with modern observation tools. Second, if hypothetical probes were released, they could use visibility reduction technologies, light-absorbing coatings, or orientation-minimizing solar reflection. Third, and this is the simplest explanation, the entire hypothesis was simply a thought experiment, and 3I Atlas truly was an ordinary comet without any artificial nature. Absence of evidence doesn't prove absence, but in science we work with what we can observe and measure. Astronomical history shows that absence of observations can be just as informative as positive results. In the 19th century, astronomers searched for planet Vulcan between Mercury and the Sun to explain anomalies in Mercury's orbit. Despite numerous observations and even several false detections, the planet was never found. Later, Albert Einstein's general theory of relativity, published in 1915, explained the anomalies without needing an additional planet. The absence of Vulcan became an important confirmation of the new physics. Similarly, the absence of probes from 3I Atlas could be important information indicating that the object follows natural laws of celestial mechanics without artificial interference. Loeb, in his subsequent comments, acknowledged that the absence of detected probes after the Venusian flyby wasn't surprising, but emphasized that the real test would come in December, when the object approaches Earth. Earth presents incomparably greater interest for any research mission than Venus, for obvious reasons. The presence of liquid water, oxygen atmosphere, a biosphere that changed the planet's chemical composition so it's visible even from space, and of course the presence of a technological civilization that radiates radio waves and light into space. If extraterrestrial intelligence wanted to send probes to study our system, Earth would be the priority target. December 19th, the date of closest approach to Earth, remained a key date on the Galileo Project's calendar. Meanwhile, observations of 3I Atlas itself continued to bring new data. Photometric measurements showed that the object's brightness slowly decreased as it moved away from the sun, which corresponds to normal comet behavior, where ice evaporation slows with increasing distance. Spectroscopic observations confirmed the presence of a standard set of molecules in the coma: water, carbon monoxide, carbon dioxide, methane, ammonia, cyanogen. The ratio of these molecules differed somewhat from what's observed in comets formed in our solar system, which isn't surprising considering 3I Atlas came from another star system where formation conditions could differ significantly. Isotopic analysis performed using high-resolution spectrographs showed an anomalous deuterium to hydrogen ratio, indicating formation in a cold environment, possibly on the outskirts of another planetary system, or even in an interstellar cloud. The question of where exactly 3I Atlas came from remained open. Backward trajectory calculation showed that the object entered the solar system at a speed of about 30 kilometers per second, relative to the local standard of rest, meaning relative to the average velocity of stars in the sun's neighborhood. The direction it came from pointed to an area of sky in the constellation Orion, but this didn't mean its home star is there now. Cosmic objects travel for millions of years, and during that time, stars shift significantly relative to each other due to proper motion. To determine the parent star, one would need to trace the trajectories of thousands of nearby stars backward in time and find the one whose trajectory intersected with the object's trajectory millions of years ago. Such analysis was performed for Oumuamua, but yielded no definitive answer, and for 3I Atlas, the results were equally uncertain. One of the mysteries of interstellar objects is how many there should be. If such objects are regularly ejected from planetary systems as a result of gravitational interactions with giant planets, then the galaxy should be filled with them. By some estimates, at any given moment, several interstellar objects should be within Neptune's orbit, but most are too dim and small for us to detect them. Oumuamua and comet Borisov were discovered because they passed close enough to the sun and became bright enough. 3I Atlas fell into the same category of lucky ones that found themselves in the right place at the right time to be noticed by our telescopes. But how many more such objects pass through the system unnoticed? And how many of them might be something more than just ice chunks? The Galileo Project was developing plans to create a network of specialized telescopes that would scan the entire sky at high frequency, specifically aimed at detecting fast-moving small objects. Such telescopes would complement existing asteroid detection systems, but with a focus on finding anomalies, objects whose behavior doesn't fit standard models. Funding such a project required significant resources, and Loeb was actively engaged in attracting private investors who shared his vision. Some critics called this a waste of resources chasing chimeras, but supporters pointed out that precisely such projects, standing at the boundary of the generally accepted, sometimes lead to revolutionary discoveries. In mid-November 2025, the scientific community received unexpected news. A group of astronomers from the European Southern Observatory published results of high-precision radar observations of 3I Atlas, performed using one of the world's largest radio antennas. Radar observations allow obtaining a three-dimensional image of an object, determining its size, shape, and rotation characteristics with precision unattainable by optical telescopes. The data showed that 3I Atlas's nucleus was about 3 kilometers long and about 1 kilometer wide, confirming its elongated shape. The surface proved unexpectedly smooth for a comet, without large craters or protrusions, which could indicate either a young surface renewed by recent activity or a composition different from ordinary comets. The rotation period was about 18 hours, which is within the norm for objects of this size. This data added new details to the portrait of 3I Atlas, but didn't resolve the fundamental question about its nature. The smooth surface could be the result of ice sublimation that smooths out irregularities, or the result of formation under special conditions. The elongated shape, though unusual, occurs in some asteroids and comets, such as asteroid Cleopatra, which resembles a dog bone, or asteroid Itokawa, which has the shape of a peanut. Nature is capable of creating the most bizarre forms without the help of intelligent design, and without additional evidence, it would be premature to make extraordinary conclusions. Science requires patience, data accumulation, multiple checks before making statements that can change our understanding of the universe and our place in it. December was approaching, the month when, according to Loeb's prediction, hypothetical probes should reach Earth's vicinity. Near-Earth space monitoring systems were operating in normal mode, tracking tens of thousands of objects, from large satellites to small fragments of space debris. If something new appeared, if any object's trajectory proved anomalous, it would be noticed. But for now, the sky remained calm, predictable, obeying the laws of Newton and Kepler that have governed the motion of celestial bodies for over 3 centuries now. And there was a certain beauty in this calmness, a reminder that space, despite all its mysteries, is mostly understandable and predictable for those who know how to read its language of mathematics and physics. December has always been a month of anticipation. In ancient times, people awaited the winter solstice, the longest night of the year, after which light begins to conquer darkness. In Christian tradition, Advent, the 4 weeks before Christmas, is dedicated to waiting and preparation. In 2025, another expectation was added to these traditional ones, less known to the general public, but significant for those following the wanderings of 3I Atlas. December 19th, the date of the comet's closest approach to Earth, stood on the Galileo Project's calendars as a day that could either close or dramatically change the direction of research. The distance was to be 1.8 astronomical units, about 270 million kilometers, far by human standards, but close by cosmic ones, close enough that any hypothetical probes, if they were released at perihelion, could reach our planet's vicinity. Near-Earth space monitoring systems developed over decades, starting in the late 20th century, when the scientific community realized that collision with a large asteroid could have catastrophic consequences. 66 million years ago, an asteroid about 10 kilometers in diameter struck the Yucatan Peninsula, creating the Chicxulub crater and causing mass extinction that ended the age of dinosaurs. In 1980, physicist Luis Alvarez and his son, geologist Walter Alvarez, published a theory linking this extinction to an impact from space, based on discovering a layer of iridium worldwide. Initially met with skepticism, this theory gained wide acceptance by the late 80s and led to understanding that similar events, though rare, pose a real threat to civilization. In 1998, the United States Congress tasked NASA with detecting 90% of near-Earth asteroids larger than 1 kilometer. This task was largely completed by 2010. Then the mandate was expanded to objects larger than 140 meters, a size sufficient to destroy a major city or create a devastating tsunami if falling into the ocean. By 2025, The catalog of known near-Earth objects included more than 35,000 asteroids, with dozens of new ones added each week. Telescopes operated automatically, photographing the same sections of sky again and again. Algorithms compared images, flagging everything that moved, and astronomers checked each detection, calculating orbits and assessing potential danger. The ATLAS system, Asteroid Terrestrial Impact Last Alert System, developed by the University of Hawaii, consisted of 4 telescopes located in Hawaii, Chile, South Africa, and on the Spanish island of Tenerife. Each telescope scanned its available sky every 2 nights, creating wide field of view images. It was this system that discovered Comet 3I Atlas on July 1, 2025, noticing an unusually fast-moving object that didn't match any known orbit. The Pan-STARRS system, Panoramic Survey Telescope and Rapid Response System, also located in Hawaii, complemented ATLAS with deeper surveys capable of detecting dimmer objects. Together, these systems created an observation network that made it almost impossible for an object larger than a few meters to approach Earth unnoticed, unless it came from the sun's direction, where observations are difficult due to bright daylight. To detect objects approaching from the sun's direction, space telescopes were being planned that would be positioned at Lagrange points of the Earth-Sun system, where gravitational forces are balanced and an object can remain stationary relative to Earth and the Sun. Such telescopes would gain the advantage of observing areas of sky invisible from Earth. The NEO Surveyor mission, whose launch was planned by NASA for the late 20s of the 21st century, was to become the first specialized space telescope for detecting potentially hazardous asteroids. But by the end of 2025, this mission was still in development, and the main burden of monitoring fell on ground-based observatories. The precision with which modern systems can determine a celestial body's orbit is astounding. After several nights of observations, astronomers can calculate an asteroid or comet's trajectory years and even decades ahead with an error margin of a few kilometers. This is achieved through precise measurements of an object's position in the sky at different moments and applying laws of celestial mechanics that account for gravitational influence from the sun, planets, and even large asteroids. Each additional observation refines the orbit, reducing uncertainty. For 3I Atlas, the orbit was determined with high precision by the end of July 2025, after a month of intensive observations. Predictions of its future position were so accurate that astronomers knew where to point telescopes to observe the object, even when it became too dim for automatic detection. But here's what's interesting. Such precision works for large objects that move only under gravity's influence. For small objects a few meters in size, sunlight pressure and solar wind can create noticeable perturbations that accumulate over time. The Yarkovsky effect, named after Russian engineer Ivan Yarkovsky, who described it in the late 19th century, manifests in how a rotating asteroid heats up from the sun on one side and then re-radiates this heat as infrared radiation when that side turns away from the sun. This creates a tiny reactive force that slowly changes the orbit. For a meter-sized object, this effect can alter the orbit by thousands of kilometers over several months. This is precisely why detecting and tracking small objects, such as hypothetical probes from 3I Atlas, presents particular difficulty. In early December 2025, the astronomical community was discussing results of a new study published in Nature Astronomy. A group of scientists from MIT conducted statistical analysis of trajectories of all known interstellar objects and extrapolated how many such objects should pass through the inner solar system each year. Their conclusions were unexpected. If we account for observational system limitations and the fact that most interstellar objects are too dim for detection, about 7 interstellar objects larger than 100 meters should pass through Earth's orbit each year. We discovered only 3 in 8 years, from 2017 to 2025, meaning we're missing the vast majority. This statistic had important implications. Interstellar space is much more populated than we thought, and our detection capabilities are still very limited. If several interstellar objects pass unnoticed each year, the question arises, what if one of them actually turns out to be artificial? What's the probability we'd detect and recognize it? Loeb in his works provided calculations showing that with current technology levels, we could detect an artificial car-sized object only if it ended up within the moon's orbit, about 400,000 kilometers. At greater distances, such objects are simply too dim. This creates a kind of paradox. We search for signs of extraterrestrial civilizations in distant galaxies using radio telescopes, but might miss their probe flying right past us simply because it's too small and dim for our instruments. Solving this paradox requires either more sensitive detection systems or a different approach to searching. The Galileo Project was developing a concept of a distributed network of small satellites in Earth orbit that would work like eyes looking in all directions simultaneously. Each satellite would carry a camera and simple image processing system capable of detecting moving objects. Data from all satellites would combine to create a three-dimensional picture of everything moving in near-Earth space. Such a system could detect objects down to several centimeters at distances up to 1 million kilometers. The cost of such a project was estimated at several $100 million, which is a lot for a private initiative but insignificant compared to many space agency budgets. The question was priorities. Is it worth investing such sums in searching for something that may not exist? Scientific history shows that investments in searching often pay off with unexpected discoveries. Radio telescopes built to study cosmic radio emission accidentally discovered pulsars, quasars, the cosmic microwave background radiation. Gravitational wave detectors, built over decades to test general relativity's predictions, opened an entirely new field of astronomy, allowing observation of black hole and neutron star collisions. The Hubble Space Telescope, launched in 1990, provided images and data that changed our understanding of the age, size, and evolution of the universe. Instruments created to answer one question often lead to discoveries in completely different areas. A system for detecting small objects in space could not only search for extraterrestrial artifacts, but also significantly improve planetary defense, help study space debris, meteor streams, and even search for new planetary satellites. By mid-December 2025, tension among the small group of enthusiasts following Loeb's prediction began to grow. Less than a week remained until December 19th, the date of maximum approach. Monitoring systems showed nothing unusual. Known object catalogs were filling with new asteroids at the usual pace, but all matched expected parameters of natural objects. No anomalous trajectories, no objects moving faster than they should given their orbits, no signs of controlled movement. The sky was calm, and for most people this was good news. But for those hoping for confirmation of the hypothesis about 3I Atlas's artificial nature, this calmness was starting to turn into disappointment. However, Loeb, in an interview he gave to the astronomy blog Universe Today on December 14th, remained philosophically minded. He reminded that science is a process of testing hypotheses, and a negative result is also a result. If hypothetical probes aren't detected, this won't prove 3I Atlas isn't artificial, but will decrease the probability of this assumption. On the other hand, even one detected probe would completely change the picture. Loeb quoted Carl Sagan, who said that absence of evidence is not evidence of absence, but added his own clarification. Nevertheless, we must search for evidence as thoroughly as our technologies allow and accept the results, whatever they may be. Scientific honesty requires readiness to be wrong and admit it. December 19th was approaching, and with it, that moment which should either confirm or refute one of the boldest predictions of recent years. In observatories around the world, telescopes were pointed at the section of sky where 3I Atlas should be. Automatic detection systems continued their work, scanning the sky for any new moving objects, and somewhere out there, in the cold darkness of space, 270 million kilometers from Earth, an ancient comet, or perhaps something completely different, continued its silent journey through our system, guarding its secrets as reliably as millennia guarded the mysteries of buried civilizations, until archaeologists uncovered them with patient labor and luck. To understand why perihelion was the ideal point for hypothetically releasing probes, we need to dive into the elegant mathematics of celestial mechanics that governs the movement of everything in space. Johannes Kepler, working in the early 17th century with data collected by his teacher Tycho Brahe, formulated 3 laws of planetary motion that remain the cornerstone of our understanding of orbits. The first law states that planets move in elliptical orbits with the Sun at one focus. The second law, sometimes called the law of areas, states that the line connecting a planet and the Sun sweeps out equal areas in equal time intervals. This means that when a planet or comet is close to the Sun, it moves fast, and when far away, slowly. The third law relates an object's orbital period to the size of its orbit through a mathematical relationship that allows predicting motion with astonishing accuracy. For 3I Atlas, arriving from interstellar space, the orbit was not an ellipse, but a hyperbola, an open curve, meaning the object makes only one pass by the Sun and then leaves the system forever. But Kepler's laws still apply in that part of the trajectory where the object is under the dominant influence of solar gravity. At the moment of perihelion on October 29th, the comet reached its maximum speed relative to the Sun, approximately 52 kilometers per second. For comparison, Earth moves in its orbit at about 30 kilometers per second. This colossal speed was key to the possibility of rapid interplanetary transfers. If a small object separates from the comet at this moment, even with a small additional velocity of a few hundred meters per second, its trajectory can be directed to practically any point in the inner solar system. Space agency engineers use similar principles when planning interplanetary missions. When NASA sent Voyager 2 in 1977 to explore the outer planets, the trajectory was carefully calculated to use Jupiter's gravity to accelerate and change direction toward Saturn, then Saturn's gravity to direct toward Uranus, and finally, Uranus's gravity to throw toward Neptune. This method, called a gravity assist or slingshot, allowed the probe to visit all 4 giant planets in 12 years, which would have been impossible with direct trajectories. Each planet acted as a kind of springboard, transferring part of its orbital energy to the spacecraft. For hypothetical probes from 3I Atlas, perihelion would play a similar role, only instead of a planet, acceleration would be provided by the parent object's initial velocity and the Sun's gravity. Loeb's calculations were based on simple ballistics. If a probe about 10 meters in size and with a mass of, say, several tons were released with a relative velocity of 300 meters per second in a direction chosen so its trajectory intersects with Earth's orbit, then flight time would be approximately 7 weeks. This assumes a ballistic trajectory without additional maneuvers or accelerations. For more precise guidance, the probe could use small corrective impulses midway, but even without them, with the right choice of initial velocity and direction, it could pass close enough to Earth to conduct observations. December 19th was the date when such a probe, released on October 29th, should reach our planet's vicinity, passing at a distance from several million to several tens of millions of kilometers, depending on guidance precision. Interestingly, reaching Earth doesn't require a straight line. In space, objects move along curved trajectories under gravity's influence, and the shortest path is often not the fastest. This contradicts our earthly intuition, where the shortest distance between 2 points is a straight line. In space, the shortest time is achieved by trajectories that use celestial bodies' gravity to accelerate and change direction. The Cassini mission, launched to Saturn in 1997, first headed to Venus, then returned to Earth, then back to Venus again, and only after that headed to the outer solar system through the asteroid belt and past Jupiter. This complex trajectory allowed the probe to gain necessary speed without using huge amounts of fuel. Nature generously offers these gravitational springboards to those who know how to use them. For a hypothetical extraterrestrial civilization that developed interstellar travel technology, such maneuvers would be child's play. But here arises an interesting paradox often discussed in the context of searching for extraterrestrial intelligence. If a civilization is advanced enough to send probes to other stars, why would it use such primitive methods as ballistic trajectories? Why not use advanced propulsion systems that would allow probes to reach planets in days or even hours? The answer may lie in the economics of interstellar travel. The energy needed to accelerate an object to high speeds grows proportionally to the square of velocity. To cut flight time in half requires 4 times more energy. Even for an advanced civilization, energy isn't infinite, and using natural orbital mechanics to save energy may be a sensible strategy. Another explanation relates to the concept of von Neumann probes, self-replicating machines named after mathematician John von Neumann, who, in the mid-20th century, theoretically described the possibility of creating such devices. If a civilization sends not one probe, but millions or billions that can reproduce themselves from materials found in other systems, then the cost of each individual probe must be minimal. Such probes would be simple, reliable, and use minimal energy. They could travel for millions of years, moving from star to star, slowly exploring the galaxy. For such probes, time doesn't matter, and using slow ballistic trajectories would be preferable to energy-intensive maneuvers. If 3I Atlas truly was a carrier of such probes, its behavior would fully correspond to the logic of maximum efficiency and minimum costs. But all this remained in the realm of speculation, intellectual exercises that help us prepare for the possibility of contact, but don't replace real observations. By mid-December 2025, reality remained stubbornly mundane. Monitoring systems continued tracking thousands of known objects and discovering new ones, but all matched expected parameters of natural asteroids and comets. The near-Earth object catalog grew, but none of the new objects showed signs of anomalous behavior. Orbits were predictable. Brightness changes corresponded to irregular shape rotation. Spectra showed ordinary rocky or icy composition. Space was exactly as we'd known it throughout centuries of astronomical observations, obedient to the laws of physics and devoid of dramatic surprises. Astronomical history is full of periods of waiting when scientists predicted events that either happened or didn't, teaching us patience and humility before nature. In 1846, astronomer Johann Galle discovered the planet Neptune using mathematical predictions by Urbain Le Verrier and John Adams, who calculated its position based on perturbations in Uranus's orbit. This was a triumph of theoretical astronomy, showing that mathematics can predict the existence of invisible objects. But not all predictions were so successful. The search for planet Vulcan, which supposedly caused anomalies in Mercury's orbit, continued for decades and led nowhere. Vulcan didn't exist, and the anomalies were explained only after general relativity was created. Loeb's prediction about probes from 3I Atlas was testable, which made it good science regardless of the result. Meanwhile, 3I Atlas itself continued moving away from the sun, gradually dimming as solar heat weakened and ice evaporation slowed. The green coma that made the comet so noticeable in summer and autumn months began to shrink and fade. By the end of December, the object would be visible only in large telescopes, and by the end of winter 2026, it would become so dim that only the most powerful instruments could track it. But the trajectory was known with high precision, and astronomers planned to continue observations as long as possible. March 16, 2026, when the comet passes close to Jupiter, would be the last opportunity for detailed observations using amplification effects, when light reflected from the object could be enhanced by passing near the bright planet. Jupiter, the giant planet whose mass is 318 times that of Earth, plays a special role in the solar system's architecture. Its powerful gravity acts as a vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise threaten the inner planets. The Shoemaker-Levy 9 event in 1994, when a comet broke into fragments and crashed into Jupiter, creating huge scars in its atmosphere visible even in amateur telescopes, reminded us of this planet's protective role. If such a comet had hit Earth, the consequences would have been catastrophic. 3I Atlas's passage by Jupiter at a distance of 0.36 astronomical units was close enough for the planet's gravity to slightly alter the comet's trajectory, but not enough to capture or destroy it. This would be the last significant gravitational maneuver before the object leaves the solar system forever. The concept of forever in a cosmic context deserves reflection. After 3I Atlas leaves the sun's influence, it will drift through interstellar space, possibly for millions of years, before approaching another star. During this time, it will cool to the temperature of the interstellar medium, about 3 Kelvin, just 3 degrees above absolute zero. No activity, no evaporation, just a cold, dark chunk of ice and rock, or, if Loeb's fantasy is correct, a dormant machine drifting while awaiting the next encounter with a star system. Time at such scales loses its usual meaning. Civilizations may rise and fall, species may evolve and go extinct, while the object continues its silent journey, indifferent to the passage of epochs. This perspective of deep time is simultaneously calming and disturbing. It reminds us of our transience as a species, and simultaneously of the potential for a future we can barely imagine. If humanity survives and develops, perhaps in thousands of years, we ourselves will send interstellar probes that will travel between stars, studying other worlds. Perhaps somewhere in the distant future, one of our probes will pass through another star's system, and it will be discovered by another civilization that will ask the same questions we're asking now about 3I Atlas. Is this strange object natural or artificial? What can it tell us about its creators? This symmetry, reflecting our current position in a possible future, gives the search special resonance. Days remained until December 19th, and the tension of anticipation began yielding to acceptance of the likely outcome. The sky kept its silence, offering neither confirmation nor refutation, only a continuing stream of ordinary data about ordinary objects following ordinary trajectories. And in this silence was its own truth, a message that the universe isn't in a hurry to reveal its secrets, that extraordinary discoveries require not only bold hypotheses, but also exceptional luck, patience, and readiness to accept what nature is willing to show, not what we want to see. The work of an astronomer in the 21st century differed greatly from the romantic image that existed in the public consciousness. There were no more solitary observers sitting in cold observatory domes, peering through telescope eyepieces and recording observations in leather journals by red lantern light. Modern astronomy became a big data science, where telescopes were controlled by computers, images processed automatically, and astronomers worked in warm offices hundreds or thousands of kilometers from the instruments, analyzing streams of information on monitor screens. Observing night turned into a sequence of emails with attached data files, Python scripts for image processing, and video conferences with colleagues from other time zones. But the essence remained the same: patient observation, systematic data collection, slow accumulation of knowledge bit by bit, one discovery at a time. Dr. Maria Hernandez, an astronomer from Cerro Tololo Observatory in Chile, was one of those who devoted a significant part of her observing time in November and December 2025 to studying 3I Atlas. She specialized in comet spectroscopy, a technique that allows determining an object's chemical composition by the spectrum of light it emits or reflects. Each chemical element and molecule leaves characteristic lines in the spectrum, a kind of barcode that an experienced researcher can read like an open book. Hernandez received her degree in 2015, defending a dissertation on the composition of Jupiter family comets, and since then had observed dozens of these icy wanderers. But 3I Atlas was special. This was an opportunity to study material formed around another star, a window into the chemistry of another planetary system that opened for only a few months while the object was bright enough for detailed observations. The night of December 14th was exceptionally clear in the Andes, which didn't happen as often as one would like. Humidity was low, atmospheric turbulence minimal, conditions almost ideal for high-resolution spectroscopy. Hernandez requested 3 hours of observing time on the 4-meter Victor Blanco telescope, and her application was approved by the Time Allocation Committee. She worked remotely from her office at La Serena University, 300 kilometers north of the observatory, controlling the telescope through a secure internet connection. On the screen before her displayed an image from the guiding camera showing the telescope's position and the gradually accumulating spectrum of 3I Atlas. Each minute of exposure added photons to the spectrum, strengthening weak lines and improving the signal-to-noise ratio. This was meditative work requiring patience and attention, but not haste. The telescope did its job while she observed, periodically checking data quality and correcting guidance. In the gradually emerging spectrum, Hernandez saw familiar lines: hydroxyl emission, a product of water breakdown under the sun's ultraviolet radiation; cyanogen lines, giving the comet a characteristic smell if anyone could get close enough to smell it; weak lines of ammonia and methane. But there were unusual details. The ratio of carbon isotopes, carbon-13 to carbon-12, was higher than in solar system comets. This indicated formation in colder conditions, possibly in a molecular gas cloud between stars, before the material was captured by a forming planetary system. Each line in the spectrum told part of the story about the ancient past, about processes that occurred billions of years ago in the vicinity of an unknown star. Hernandez took notes, planning analysis that would take weeks after observations concluded. But right now she was simply collecting data, photon by photon, building a bridge between a distant star system and human understanding. Meanwhile, on the other side of the world, in the Galileo Project laboratory in Cambridge, Massachusetts, a small team of analysts was reviewing the latest data from near-Earth object detection systems. Their task was identifying anomalies, objects that didn't fit standard categories. Most new detections were routine. Main belt asteroids discovered yet again because their orbits brought them into a sky region not observed frequently enough. Near-Earth asteroids already known, but requiring orbital element updates. Satellites, space debris, sometimes meteors captured at the moment of atmospheric entry. Machine learning algorithms trained on thousands of examples automatically classified most objects, flagging for human analysis only those whose characteristics exceeded certain thresholds. For the week from December 7th to 14th, 43 new objects were discovered, all classified as natural asteroids. None showed signs of anomalous trajectory or behavior. Dr. Amir Siraj, an astrophysicist and postdoctoral researcher working with Loeb on the Galileo Project, felt no disappointment from these results. He understood that the probability of detecting an artificial object was extremely small, even if they exist. Space is vast, objects are small, and our detection capabilities are limited. But the search process itself had value. Each observation, each analyzed object added to our understanding of the solar system's small body population. Data collected in attempting to find extraterrestrial artifacts also served to improve planetary system formation models, assess Earth collision risks, and plan future space missions. Science is rarely straightforward. Often the most important discoveries are made not where we expected them, and not by the methods we plan to use. Flexibility and openness to the unexpected were key qualities of a good researcher. Siraj recalled a conversation he had with Loeb several weeks ago when they discussed possible outcomes of testing the probe hypothesis. Loeb said something that stuck in memory. "We're in a privileged position. We live in a moment of history when we first possess the technology to detect signs of extraterrestrial life or technology, if they exist in our accessible region of space. Our ancestors could only dream and fantasize. Our descendants will perhaps know the answer, but we stand on the boundary, at the moment of transition from ignorance to knowledge. And this demands special responsibility from us. We must search honestly, thoroughly, not allowing either skepticism or enthusiasm to obscure objectivity. If we find something, it must withstand the strictest scrutiny. If we don't find anything, we must honestly admit it and continue improving search methods." These words reflected the philosophy guiding the Galileo Project's work. The search for extraterrestrial intelligence was often criticized as pseudoscience or, at best, a very speculative endeavor with low probability of success. But Loeb and his team approached it with full scientific rigor. They published their methods, shared data, invited criticism and verification. They didn't make extraordinary claims based on weak evidence. Instead, they systematically built infrastructure for searching, developed tools, trained the next generation of researchers, and patiently accumulated data. If extraterrestrial artifacts exist in our cosmic neighborhood, this methodology would eventually detect them. If they don't exist, at least we'd know we searched as thoroughly as our technology allowed at this stage of development. Scientific history shows that persistence is often rewarded, but not always as expected. Michael Faraday spent decades experimenting with electricity and magnetism in the first half of the 19th century, before discovering electromagnetic induction, a phenomenon that became the foundation of all modern electrical engineering. Marie Curie and her husband Pierre processed tons of uranium ore in primitive conditions in the late 19th century before isolating radium and polonium, opening the era of nuclear physics. Jocelyn Bell Burnell analyzed kilometers of paper tape with radio telescope recordings in 1967 before noticing regular pulses that turned out to be the first discovered pulsar. All these discoveries required not only intellect and intuition, but almost superhuman patience, readiness to do routine work month after month, year after year, not knowing whether it would lead to something significant. The approach of December 19th had symbolic significance extending beyond Loeb's specific prediction. This was a point around which crystallized reflections about our place in the universe, about the probability of other civilizations' existence, about the methods we use to search for them. The Fermi paradox, formulated by physicist Enrico Fermi in 1950, asked the question, If alien civilizations exist, and if some are much older than us, then where is everyone? Why don't we see obvious signs of their presence? Over 75 years, many answers to this paradox were proposed. Perhaps life is extremely rare. Perhaps technological civilizations are short-lived and self-destruct. Perhaps interstellar travel is practically impossible. Perhaps we're simply looking in the wrong place or the wrong way. Loeb offered another explanation. Perhaps we simply haven't looked carefully enough. Until recently, we didn't have the technology to detect small objects at large distances with sufficient sensitivity. Oumuamua was detected only because it passed very close, and even then, we saw it only on the way out, when it was already receding. If similar objects regularly pass through the solar system, but farther from the sun or smaller in size, we simply don't notice them. It's like searching for a needle in a haystack when you only have a handheld metal detector that works at a distance of a few centimeters. You can search for years and find nothing. Not because the needle isn't there, but because the haystack is huge and your tool isn't sensitive enough. The solution isn't to stop searching, but to develop better tools. By December 15, 2025, discussions began in the astronomical community about next steps in studying 3I Atlas after it becomes too dim for ground-based observations. Some proposed using the James Webb Space Telescope, humanity's most powerful infrared telescope launched in late 2021. In the infrared range, the comet could be visible longer since it emits its own thermal radiation, not just reflects sunlight. Others suggested attempting to detect radio emission from the object, though natural comets don't radiate in the radio range, except for very weak thermal noise. Still others talked about the possibility of sending a fast space probe to intercept 3I Atlas, while it's not yet too far. But such a mission would require many years of preparation and enormous financial costs, and could hardly be approved without more convincing evidence of the object's unusual nature. The reality of space missions is that they're planned years, sometimes decades before launch. An idea must be proposed, evaluated by scientific committees, funded by government agencies or private investors, designed by engineers, built, tested, and only then launched. The New Horizons mission to Pluto, launched in 2006, was planned since the 1980s. The Cassini mission to Saturn, launched in 1997, was developed from the early 80s. For an interstellar object that passes through the system in several months and then disappears forever, such a timescale is unacceptable. New approaches are needed, perhaps permanent spacecraft on standby that can be quickly redirected to interesting objects. But such concepts remained in the realm of preliminary studies and weren't implemented by 2025. On the night of December 16th, amateur astronomer Thomas Kraus from a Munich suburb pointed his 20-centimeter telescope at the coordinates where, according to ephemerides, 3I Atlas should be. Kraus was a retiree, a former engineer who devoted the last 20 years of his life to astronomy as a hobby. He built his observatory in the backyard, a small dome with an automated telescope and CCD camera. Every clear night, he observed something: variable stars, asteroids, comets, galaxies. His observations were regularly submitted to international databases, where they were used by professional astronomers to refine orbits and object characteristics. Amateur astronomy in the 21st century became a serious contribution to science, complementing the work of professional observatories and sometimes making important discoveries. Kraus took a series of 20 images with 2-minute exposures each. After processing and alignment, he saw a faint, blurry spot at 3I Atlas's expected position. The comet was barely visible even after summing all frames, but it was there. Kraus measured its position with accuracy to an arcsecond and sent a report to the Minor Planet Center of the International Astronomical Union, the organization that coordinates asteroid and comet observations worldwide. His observation joined thousands of others, slowly refining the object's orbit, adding tiny details to our understanding of its motion. On the scale of all science, this was a microscopic contribution, but it's precisely from such contributions, multiplied by thousands of observers and millions of observations, that the edifice of human knowledge about space was built. On December 17, 2025, the world plunged into pre-Christmas bustle that captures cities and villages every year at this time. Store windows sparkled with lights, Christmas trees were being set up in squares, people rushed with gift shopping and holiday gathering plans. In this flow of everyday life, only a few remembered that somewhere out there, in the cold darkness beyond the atmosphere, an event was unfolding that could change our understanding of our place in the universe. For the overwhelming majority of humanity, 3I Atlas remained an obscure entry in astronomical catalogs, an object that may have been mentioned in science news several months ago, but got lost among thousands of other events demanding attention. But for a small group of scientists, students, and space enthusiasts around the world, these days were filled with special tension, a mixture of hope and sober understanding of probabilities. In online communities dedicated to astronomy and the search for extraterrestrial life, activity noticeably increased. Reddit forums, specialized Discord servers, social media groups discussed Loeb's prediction with varying degrees of seriousness. Some participants conducted their own trajectory calculations using publicly available data on 3I Atlas's orbit and physical models of small body motion. Others shared links to live streams from observatories that could be watched in real time, though for an unprepared viewer, these streams represented only slowly drifting star fields without visible drama. Still others plunged into philosophical reflections about the meaning of possible contact, about how it would change society, religion, politics. The spectrum of opinions was wide, from convinced skeptics who considered the whole story another sensation without foundation, to enthusiasts already planning how humanity should respond to a message from the stars if it came. On December 18th, Avi Loeb published a short note on his Medium blog, a kind of preamble to the expected result. He wrote about the importance of impartiality in science, about how a negative result is also a result with scientific value. He reminded readers that his prediction was not a forecast in the direct sense, but a demonstration of how unusual hypotheses can be tested through observations. If probes aren't detected, this won't prove 3I Atlas isn't an artificial object, but will make this hypothesis less probable. On the other hand, detecting even one object with an anomalous trajectory would immediately require intensive follow-up observations and analysis. Loeb concluded the note with a quote from Carl Sagan. "Somewhere, something incredible is waiting to be known." This phrase reflected the essence of scientific search, the mixture of patience and curiosity that drives researchers through years of routine work in hope of a moment of revelation. On the night of December 18th to 19th, observatories in the southern hemisphere had optimal conditions for observing the sky region where hypothetical probes were expected, if they existed and followed predicted trajectories. Automated detection systems, Atlas, Pan-STARRS, and others operated in normal mode, their algorithms unaware that this day was special for someone. They simply continued doing what they did every night, photographing sections of sky, comparing new images with previous ones, flagging objects that changed position. Over the night, systems processed hundreds of thousands of images covering most of the accessible sky. Algorithms identified several dozen moving objects, most of which were known asteroids at expected positions. Several objects were new discoveries, but their orbits were quickly calculated and classified as ordinary main belt asteroids or near-Earth objects. None showed signs of a trajectory that could correspond to a launch from 3I Atlas in late October. The morning of December 19th in Cambridge, Massachusetts, began with gray skies and light snow, the first of the season. In the Galileo Project office, a small team gathered over cups of coffee, reviewing night data that gradually arrived from various observatories and monitoring systems. The atmosphere was businesslike, without drama. Everyone understood that the probability of detecting something unusual was extremely small, and no one built unrealistic expectations. But data checking was still conducted thoroughly, each object analyzed, each trajectory calculated. By noon Eastern Time, it became clear that night observations brought nothing anomalous. Catalogs were supplemented with several new asteroids, orbits of several known objects were refined, but no signs of probes moving from 3I Atlas toward Earth were detected. December 19th passed as an ordinary day in the life of astronomical research, without sensations and revelations. It's important to understand that absence of detection didn't mean probes definitely aren't there. Limitations of modern observation systems are such that objects smaller than a meter are virtually impossible to detect at distances of millions of kilometers. If hypothetical probes were smaller than this size, or if they used visibility reduction technologies, they could pass unnoticed. Moreover, the accuracy of trajectory prediction depended on numerous assumptions about initial velocity, launch direction, probe mass. Small deviations in any of these parameters could shift the arrival date by several days or weeks in either direction. So technically, December 19th wasn't an absolute deadline after which the hypothesis automatically gets disproven. This was the central date in a probability window stretching roughly from mid-December to early January. But symbolically, this was a moment of truth, a reference point for evaluating the hypothesis. By the evening of December 19th, news agencies that followed the story began publishing notes with headlines like "Alien probes didn't arrive for Christmas" or "Harvard astronomers' prediction didn't pan out." The tone of most articles was slightly ironic, with a shade of "we told you so," characteristic of coverage of speculative scientific hypotheses that aren't confirmed. Some journalists use the story as an occasion to discuss the broader topic of searching for extraterrestrial life, the Fermi paradox, SETI efforts to detect radio signals from other civilizations. Others focused on Loeb's personality, his controversial reputation in the scientific community, his previous statements about Oumuamua. The general message was, another bold hypothesis from a well-known astronomer wasn't confirmed by observations, which isn't surprising given the extraordinary nature of the claim. Life goes on, space remains mysterious, but for now silent. In the scientific community, the reaction was more restrained and diverse. Many astronomers who were skeptical from the start about the idea of 3I Atlas's artificial nature perceived the absence of detection as expected confirmation of their position. They pointed out that all observed characteristics of the object correspond to a natural comet of interstellar origin, and there's no need for more exotic explanations. However, some noted that Loeb's approach itself, formulating a testable hypothesis and attempting to test it through observations, was scientifically correct, even if the result proved negative. Science progresses not only through hypothesis confirmation, but also through their refutation, which helps us narrow the space of possibilities and focus on more probable explanations. In this sense, efforts to test the prediction weren't in vain, even if the romantic idea of visiting alien probes didn't materialize. On December 20th, Loeb gave an interview to astronomy publication Sky and Telescope, where he commented on the results. He acknowledged that probes weren't detected at the expected time, but emphasized several important points. First, the observation window hadn't completely closed yet, and it's worth continuing monitoring for several more weeks. Second, even if this specific hypothesis about 3I Atlas isn't confirmed, the general idea about the necessity of systematic search for signs of extraterrestrial technology remains important. Humanity is only beginning to develop tools and methodology for such a search, and we should expect many negative results before possibly a positive detection is made. Third, 3I Atlas itself remains an object of great scientific interest regardless of the question about its nature. Each interstellar object is a window into other planetary systems, and detailed study of such objects helps us understand the diversity of conditions in the galaxy. In the interview, Loeb also raised a broader philosophical question about the nature of scientific skepticism. He distinguished between healthy skepticism, which requires good evidence before accepting unusual claims, and dogmatic skepticism, which rejects entire research directions as unworthy of attention. The first approach strengthens science, the second limits it. History is full of examples where ideas initially rejected as absurd later proved correct. Meteorites, which in the 18th century were considered superstition. Continental drift, ridiculed when first proposed. Bacteria as the cause of stomach ulcers, for which Barry Marshall and Robin Warren received the Nobel Prize in 2005. Overcoming decades of skepticism, Loeb didn't claim his hypothesis about 3I Atlas was in the same category, but called on colleagues to remain open to testing unusual ideas as long as they're formulated in a scientifically correct manner. On December 21st, the day of winter solstice, the longest night in the Northern Hemisphere, a group of amateur astronomers in Australia organized an observation session dedicated to 3I Atlas. About 20 people gathered in rural countryside far from city lights with various telescopes, from small 8-inch to half-meter Dobsonian reflectors. The comet was barely visible, even in large instruments, a faint blurry spot against the star field, indistinguishable from a distant galaxy without knowing exact coordinates. But participants patiently aimed telescopes, took photographs, exchanged impressions. For them, this was not so much a search for signs of alien civilization as an opportunity to touch something that came from beyond our solar system, an ancient object that formed under completely different conditions and now passed by, offering a brief chance for observation. This was a celebration of the very act of observation, human curiosity, and the ability to see beyond the obvious. In the following days of December, monitoring systems continued their work, but with each day, it became increasingly obvious that no anomalous objects connected to 3I Atlas would be detected. Near-Earth object catalogs filled at the usual pace. Astronomers continued refining orbits and characteristics of thousands of known asteroids. The sky remained predictable, ordered, obeying laws of celestial mechanics without surprises and deviations. This calmness, which for some was disappointment, for others was consolation. It reminded of the reliability of the scientific method, that our models of reality are basically correct, that we understand how space works in its everyday manifestations. Extraordinary events are rare by definition, and most scientific work consists of systematic study of the mundane, slow accumulation of knowledge bit by bit. December 25th, Christmas, passed without cosmic gifts to humanity that Loeb half-jokingly wrote about in his October essay. Families gathered at holiday tables, children opened presents, cities glowed with lights. And somewhere beyond lunar orbit, in the cold void between Earth and Mars, 3I Atlas continued its silent journey toward the outer regions of the solar system. Its green coma almost completely disappeared. Activity ceased. The object returned to the state of frozen rest in which it will spend the next millions of years, drifting through interstellar space. If viewed through a telescope, it was now indistinguishable from an asteroid, a dark chunk of ice and rock reflecting a tiny fraction of light falling on it. All the dramas and speculations that unfolded around it on Earth didn't concern it. It simply was, existed, moved along a trajectory determined by laws of physics, indifferent to our hopes and interpretations. By the end of December 2025, the story about the probe prediction began disappearing from news cycles, displaced by other events. In the astronomical community, discussions began about papers summarizing observations of 3I Atlas for the entire period of its visibility. Dozens of research groups around the world collected extensive data: spectra, photometry, radar images, polarimetry. This data would be analyzed for months and years, generating scientific publications, dissertations, new models of comet formation and evolution in different planetary systems. In this sense, 3I Atlas already made a significant contribution to science, regardless of whether it was simply a comet or something more exotic. Each interstellar object expands our understanding of how diverse conditions in the galaxy can be, what variations are possible in the composition, structure, and evolution of small bodies. January 2026 began with cold, clear nights in the southern hemisphere, ideal for astronomical observations. 3I Atlas continued its journey toward the outer regions of the solar system, gradually dimming as it moved away from the sun. Its apparent magnitude dropped below the 20th, meaning only the world's largest telescopes could still distinguish it against the star field. For most observatories, the comet moved into the category of objects requiring special observing time requests and serious justification of the scientific value of continuing observations. But several research groups continued tracking the object, knowing that each additional observation improved orbital determination, accuracy, and could reveal unexpected details in its behavior or composition. Dr. Karen Meach, an astronomer from the University of Hawaii leading one such group, received time on the Subaru telescope on Mauna Kea for a series of observations in early January. Subaru, an 8-meter telescope built by Japan and commissioned in the late 90s of the 20th century, remained one of the most powerful instruments for studying faint objects. With it, one could observe galaxies at the edge of the visible universe, exoplanets around distant stars, and of course small bodies of the solar system. Meach specialized in studying comet surfaces, trying to understand how solar radiation changes their structure and composition. 3I Atlas represented a unique opportunity to study a surface that formed in another star system and then was modified by traveling through interstellar space before being exposed to our sun. The obtained spectra showed an interesting detail. The ratio of orthowater to parawater, two forms of the water molecule differing in the orientation of nuclear spins of hydrogen atoms, was anomalous. In solar system comets, this ratio is usually close to 3:1, corresponding to formation temperature around 25-30 Kelvin. In 3I Atlas, the ratio was closer to 2:1, indicating formation at even lower temperature, possibly around 15 Kelvin. This was indirect evidence that the comet's material formed in the very cold outer regions of another planetary system, possibly analogous to our Oort cloud, the hypothetical sphere of icy objects surrounding the sun at distances up to 1 light-year. Each such detail added strokes to the portrait of conditions in another part of the galaxy, expanding our understanding of possible planetary system diversity. By mid-January, the astronomical community's attention began gradually shifting from 3I Atlas to other objects and events. A new NASA mission to Uranus's moons was being planned. Multi-year exoplanet observation results from the James Webb Telescope were being announced. An astrobiology conference in Tokyo was being prepared. The rhythm of science demanded constant forward movement, and although 3I Atlas remained an object of research, it was no longer in the spotlight. This is the natural cycle of scientific interest. A flash of excitement at discovery or unusual event, a period of intensive observations and analysis, gradual decline of activity as the object becomes less accessible, or other topics require resources. But data collected over months of observations would be processed for years, generating publications and dissertations that would slowly integrate knowledge about 3I Atlas into the broader context of planetary science. In February 2026, the Galileo Project published a technical report summarizing results of near-Earth space monitoring from late October through late January. The report detailed search methodology for anomalous objects, sensitivity of detection systems used, statistical analysis of detected objects. The main conclusion was straightforward. No objects with trajectories indicating launch from 3I Atlas were detected within observational system sensitivity. This didn't completely exclude the possibility of such objects' existence, but established an upper limit on their size and reflectivity. If probes existed, they must have been smaller than a meter in diameter, or had very low albedo, reflecting less than 1% of incident light. The report also offered recommendations for improving detection systems for future cases of interstellar objects passing through the inner solar system. These recommendations were practical and detailed. First, deployment of space telescopes at Lagrange points to cover sky regions inaccessible from Earth. Second, increasing sky survey frequency from every 2 nights to daily scanning for faster detection of new objects. Third, development of more sensitive detectors capable of detecting objects 2 to 3 magnitudes fainter than current systems. Fourth, creation of an international response network that could quickly coordinate observations of unusual objects by all available instruments. Each of these recommendations required significant investment, but collectively they could transform our detection capabilities not only for potentially hazardous asteroids, but also for possible extraterrestrial technology artifacts, if they exist. March 16, 2026, the date of 3I Atlas's closest approach to Jupiter, was the last significant event in the comet's trajectory through the solar system. The distance would be 0.36 astronomical units, about 54 million kilometers. This was close enough for Jupiter's gravity to slightly alter the comet's trajectory, adding a small component to its exit velocity from the solar system. For astronomers, this was the last chance to observe the object against something bright, using contrast to improve image quality. Several observatories scheduled observations for this period, though technically it was challenging. The object was very dim, and Jupiter's brightness created interference, requiring careful processing to extract the weak comet signal. Jupiter itself represented a cosmic laboratory of incredible complexity. Its atmosphere, consisting mainly of hydrogen and helium with traces of methane, ammonia, and other compounds, demonstrated dynamics that meteorologists were only beginning to understand. The Great Red Spot, a giant anticyclone larger than Earth, had raged in the planet's southern hemisphere for at least 350 years, since astronomer Giovanni Cassini first observed it in 1665. Auroras at Jupiter's poles were hundreds of times more powerful than Earth's, created by interaction of the planet's magnetic field with charged particles from the volcanic moon Io. The system of 80 known moons formed a miniature planetary system, where the 4 largest moons discovered by Galileo Galilei in 1610 represented independent scientific interest. 3I Atlas's flyby of Jupiter was an insignificant event by the planet's standards. A small, icy chunk passing at a distance of many millions of kilometers couldn't have any influence on the giant. But for the comet, this was the last substantial gravitational interaction before exiting the zone of planetary influence. After Jupiter, only the distant ice giants Uranus and Neptune remained, but 3I Atlas's trajectory didn't pass close to them. The object moved at an angle to the ecliptic plane, the path along which most planets move, and gradually rose above this plane, heading toward interstellar space. By the end of March, it would cross Saturn's orbit, by mid-year reach Uranus's orbit, and by the end of 2026 would be somewhere between the orbits of Uranus and Neptune, already virtually untrackable even by the most powerful telescopes. In April 2026, several research groups published papers in leading astronomy journals summarizing 3I Atlas observations. One of the most cited papers appeared in Nature Astronomy, authored by an international team of 37 astronomers. The paper presented complete analysis of orbit, chemical composition, and physical characteristics of the object. The main conclusion was unambiguous. 3I Atlas was a natural comet of interstellar origin, by all observable parameters not different from expected characteristics of such objects. The unusual shape was explained by specific formation and evolution conditions. The green coma was the result of standard photochemical processes. The absence of observable rotation was explained by its orientation relative to Earth. The paper didn't mention Loeb's hypothesis about the object's artificial nature, focusing on scientific data and their interpretation within generally accepted theories. Loeb published his own paper in the more specialized Journal of Astrobiology, where he analyzed the experience of testing the hypothesis about probes from 3I Atlas. He acknowledged that the prediction wasn't confirmed within modern detection system sensitivity, but emphasized the value of the approach itself. Formulating testable hypotheses about possible manifestations of extraterrestrial technology and systematically testing these hypotheses through observations represents correct scientific method. Negative results are informative. They narrow the space of possibilities and help direct future searches. Loeb also discussed philosophical aspects of searching for extraterrestrial intelligence, arguing that conservatism in science, though important, shouldn't transition into a priori rejection of entire research directions. History shows that breakthroughs often occur when someone is willing to explore ideas that seem marginal to contemporaries. Reaction to Loeb's paper was predictably divided. Some colleagues praised him for willingness to put forward bold hypotheses and subject them to testing, seeing this as an example of how science should work. Others criticized him for attracting excessive attention to speculative ideas, potentially undermining public trust in astronomy as serious science. Still others simply ignored the entire discussion, considering it a distraction from more productive research directions. This spectrum of reactions reflected broader tension in the scientific community between the need for innovation, which requires readiness to explore unusual ideas, and the need for reliability, which requires conservatism in interpretations. The balance between these tendencies determines the pace and direction of scientific progress. By May 2026, 3I Atlas practically disappeared from news and even from specialized astronomical discussions, except for a narrow circle of researchers continuing to analyze collected data. The object became part of history, one of 3 interstellar objects discovered by humanity at that point, each with its own unique story. Oumuamua, the first, remained a mystery due to lack of observations and unusual acceleration. Comet Borisov was understandable and predictable, behaving like an ordinary comet. 3I Atlas occupied an intermediate position, unusual enough to provoke intense discussions, but not anomalous enough to revolutionize our understanding. It became a teaching example of how the scientific community works with uncertainty, how hypotheses are formulated and tested, how consensus is reached through data accumulation and critical analysis. In summer 2026, the Galileo Project announced plans to deploy the first network of small satellites for near-Earth space monitoring. Private investors agreed to fund the project's first phase, which included launching 12 CubeSat-sized satellites equipped with wide-angle cameras and automatic image processing systems. Satellites would be placed in various orbits to ensure complete sky coverage. Launch was planned for late 2027, meaning another year and a half of development, testing, and preparation. If the system proves successful, it could be expanded to several hundred satellites, creating a truly global observation network. This was a concrete result of the experience with 3I Atlas, realization that our current detection capabilities are insufficient, and willingness to invest in their improvement. In September 2026, a conference was held in Stockholm dedicated to interstellar objects and methods of studying them. More than 200 astronomers from 30 countries gathered to exchange results, discuss future research directions, and coordinate efforts. 3I Atlas was one of the central topics, with several sessions devoted to analyzing its characteristics and lessons learned from observations. The general consensus was that humanity needs a rapid response strategy for detecting future interstellar objects. Statistical models predicted that such objects should pass through the inner solar system roughly once a year, but most are too dim for detection by modern means. Improving survey capabilities should increase detection frequency, and the scientific community must be ready to maximize every such opportunity. One proposal discussed at the conference was the concept of interceptors, small spacecraft on standby in orbit that could be quickly sent to interesting objects for close approach and detailed study. Such a craft would carry cameras, spectrometers, possibly even a sample collection system for return to Earth. The project cost was estimated at several $billion, requiring international cooperation and multi-year planning. But the experience with Oumuamua, which was detected only when already receding, and the lack of detailed data it left behind, convinced many of the necessity of such capability. If the next interstellar visitor proves truly anomalous, it would be tragic to miss the chance to study it simply due to lack of readiness. By the end of 2026, 3I Atlas was somewhere between the orbits of Uranus and Neptune, a cold, dark point moving at about 30 kilometers per second relative to the Sun. Its last recorded observation was made in October 2026 using the Hubble Space Telescope at maximum exposure. After that, the object became too dim even for this legendary instrument. The trajectory was known with sufficient accuracy to predict position decades ahead, but no one would be able to see it anymore. The comet returned to that state of anonymity in which it spent millions of years before its brief visit to the Sun, and will continue its journey through the void, invisible and unknown, until in tens or hundreds of thousands of years, it approaches another star, where perhaps other observers will notice it and ask themselves the same questions about its nature and origin. A year passed since the day 3I Atlas went through perihelion, and the astronomical community had the opportunity to look back and assess the entire story with some emotional distance. October 2027 brought typical autumn weather to the northern hemisphere. Leaves changed colors. Days grew shorter, and observatories began the season of long observing nights. For most astronomers, the 3I Atlas story became part of the past, an interesting episode that spawned several dozen scientific publications and numerous discussions, but didn't revolutionize our understanding of the universe. The object was classified as a natural comet and took its place in catalogs alongside thousands of other small bodies, each with its own trajectory and characteristics. But for a small group of researchers associated with the Galileo Project and the search for extraterrestrial intelligence, the experience left a deep mark, forcing a rethinking of methods, expectations, and the very philosophy of the search. One of the most important lessons was reassessing what constitutes proof in the context of searching for extraterrestrial technology. In ordinary science, we deal with phenomena that can be repeatedly observed, experimented with, tested under controlled conditions. A physicist can repeat an experiment as many times as necessary to achieve statistical significance. A chemist can synthesize a compound again and again, testing its properties. A biologist can culture cells, observing their behavior under various conditions. But an astronomer studying a unique cosmic event, such as the passage of an interstellar object, has only one chance. The object appears, passes through the system in several months, and disappears forever. There's no possibility to repeat the observation, test an alternative hypothesis with better instruments, return and collect data that was missed the first time. This creates a fundamental asymmetry between astronomy and other sciences, requiring a special approach to data interpretation. In the case of 3I Atlas, the absence of detected probes couldn't definitively refute the hypothesis about the object's artificial nature, however strange that may sound. There always remained the possibility that probes were released, but were too small for detection, or used visibility reduction technologies, or were directed not toward Earth, but toward other targets in the system. Strictly speaking, proving the object isn't artificial was as impossible as proving the opposite without direct evidence like radio signals or obvious structural features incompatible with natural processes. This led to a philosophically unsatisfactory situation where the question remained open regardless of observation results. Karl Popper would call such a hypothesis unfalsifiable, which in his system disqualified it as scientific. But Loeb and other researchers argued that in the context of unique cosmic events, a more flexible epistemological approach is required. The alternative was using Bayesian probability, a mathematical method of updating degree of confidence in a hypothesis based on new data. In the Bayesian approach, we start with a prior probability, our initial assessment of how likely a hypothesis is before obtaining data. Then update this probability based on observations, obtaining a posterior probability. For the hypothesis about 3I Atlas's artificial nature, the prior probability was extremely low, perhaps one chance in a million or less, based on the absence of previous detections of extraterrestrial artifacts. Observations showed that all characteristics of the object were compatible with natural origin, which further reduced the probability. But it didn't drop to zero, because it's impossible to completely exclude the possibility that highly advanced technology might mimic natural processes or simply be subtle enough that our instruments wouldn't distinguish it. The posterior probability remained very low, but not zero, leaving the door open for future research if new data appeared. This discussion may seem excessively academic, a dive into the subtleties of philosophy of science without practical significance, but in fact, it had direct consequences for how future searches were planned and funded. If absolute proof was required before a hypothesis is taken seriously, then the search for extraterrestrial intelligence would never receive funding because the probability of quick success is too small. But if it was recognized that science can work with probabilities and gradual accumulation of indirect evidence, then space opened for long-term research programs that might not produce results for decades, but could one day lead to revolutionary discovery. The SETI project, searching for extraterrestrial intelligence through detecting radio signals, operated on this model since the 1960s, not discovering a single confirmed signal in over 60 years, but continuing the search, based on the logic that absence of detection so far doesn't mean detection is impossible in the future. Another important lesson concerned the nature of public attention and scientific communication. The story about the probes by Christmas prediction received significant media coverage, attracted broad public attention, generated numerous discussions among both professionals and amateurs. This was positive in the sense that it raised awareness about interstellar objects, about the work of planetary defense systems, about astronomical research methods. Many people who never thought about these topics suddenly started following astronomy news, asking questions, getting interested in science. This was the mission of science popularization that Carl Sagan considered the most important duty of scientists. But there was also a negative side. When the prediction wasn't confirmed, some media presented it as a failure, another example of scientists making sensational claims without basis. This could undermine trust in science among part of the public, strengthen skepticism, not healthy, but cynical. The attitude that all this is just games of academics detached from reality. Loeb reflected on this in his writings, which he continued publishing on Medium. He acknowledged that communication was imperfect, that some media distorted his words, turning a careful thought experiment into an allegedly confident prediction of alien visitation. But he also defended the necessity of public discussion of scientific hypotheses, even speculative ones, as part of healthy scientific culture. Science shouldn't be an esoteric pursuit, accessible only to the initiated. It belongs to all humanity, and people have the right to know what and how is being researched with their money, whether government or private funding. Transparency breeds trust, and in the long term, a society that understands and values science is more likely to support it, even when results don't come quickly or turn out different than expected. This was a delicate balance requiring communication skills not always taught in scientific programs, but becoming increasingly important in the era of social media and instant information dissemination. The third lesson concerned the importance of infrastructure for rapid response. The experience with 3I Atlas showed that even with a developed asteroid detection system, humanity was poorly prepared for detailed study of a rapidly passing interstellar object. The object was discovered in July, reached perihelion in late October, and by year's end was already too dim for most telescopes. 4 months of intensive observations yielded enormous amounts of data, but many questions remained unanswered. Ideally, there would be a spacecraft ready for launch that could intercept the object for close approach and detailed study. But such missions require years of planning and construction. By the time a mission would be approved and built, the object would have long since left the system. The solution could be so-called standby spacecraft in ready state in orbit, capable of quickly heading toward any interesting target. The concept is technically feasible but requires constant investment in maintaining spacecraft readiness, which is difficult to justify when interesting targets appear only once every few years. The European Space Agency began preliminary studies of such a concept called Comet Interceptor, a mission that would wait in orbit for detection of a new long-period comet or interstellar object, then quickly head toward it for study. Launch was planned for the early 30s of the 21st century. This was a first step toward creating rapid response infrastructure, but the path was long. Ideally, what was needed was a network of such craft covering various possible trajectories with different scientific instruments for different types of targets. This was a long-term program that could take decades to build, but experience with Oumuamua and 3I Atlas made the necessity of such a program increasingly obvious. Each missed interstellar object was a lost opportunity to study material from another star system, a window into conditions we can't reproduce in laboratories or observe in our own system. In March 2027, an event occurred that added a new twist to the discussion about interstellar objects. Astronomers discovered a fourth interstellar object, temporarily designated 4I, entering the solar system. This time, detection happened much earlier on its trajectory, when the object was still beyond Jupiter's orbit, giving months for observation planning. First data showed it was an asteroid, not a comet, showing no signs of activity even when approaching the Sun. This was interesting in itself, since interstellar asteroids should theoretically exist, but hadn't been confidently identified until now. The scientific community mobilized to maximize this opportunity, applying lessons learned from observations of previous objects. The Galileo Project immediately included 4i in its monitoring program, and this time detection systems were more sensitive thanks to improvements implemented over the previous year. Observations of 4i continued for several months and brought interesting results. The object was significantly darker than any known solar system asteroid, with albedo around 2%, meaning it reflected only a tiny fraction of incident light. Spectral analysis showed presence of complex carbon compounds, possibly organic molecules, though definitely not biological. The shape was close to spherical, which is unusual for asteroids that usually have irregular shape due to collisions and gravitational perturbations. Rotation period was about 10 hours. All these characteristics were intriguing, but not anomalous enough to require extraordinary explanations. The consensus was 4i was a natural asteroid ejected from another planetary system, possibly from an analog of the Kuiper Belt, the region beyond Neptune where icy and rocky bodies are located. Its dark surface was the result of millions of years of irradiation by cosmic rays in interstellar space, a process that gradually changes the chemical composition of surface layers. The discovery of 4i had statistical significance. Now humanity had 4 confirmed interstellar objects in 10 years, from 2017 to 2027. This allowed refining models of interstellar space population with such objects. Extrapolation showed that at any moment, about 10 interstellar objects larger than 100 meters should be within Neptune's orbit. The vast majority pass unnoticed due to limitations of our detection systems. As telescopes and data processing methods improved, detection frequency should increase. It was predicted that by the end of the 30s of the 21st century, we'd be detecting several interstellar objects each year. This opened exciting prospects for comparative planetology, studying how conditions differ in different planetary systems and what this says about planet and star formation processes. By autumn 2027, exactly 2 years after 3i Atlas's perihelion, the story began gaining certain closure in the minds of those who lived through it. The object came from darkness, passed through our system, offering a brief window for observations and reflections, and returned to darkness, taking with it all secrets it might have revealed with closer study. There was no dramatic revelation, confirmation of extraterrestrial intelligence existence, proof that we're not alone. There was only another data point in the endless process of scientific cognition, another pebble added to the growing pyramid of human knowledge about space. And in this was its own deep beauty and significance. Science doesn't always, not even often, bring instant revolutionary discoveries. Most of the time it consists of patient observation, systematic data collection, gradual model refinement. But it's precisely this meticulous work that creates the foundation on which sometimes, in fortunate moments, towers of transforming insights are erected. For those who followed the 3i Atlas story from the beginning, who hoped for confirmation of the probe hypothesis, the result might have seemed disappointing. But with time passing, many came to understand that the very process of waiting, observing, analyzing, had value regardless of the result. It reminded how vast space is, how small our knowledge, how much remains to be discovered. It showed that the scientific community is capable of seriously considering even extraordinary hypotheses, testing them with due thoroughness, and accepting results with intellectual honesty. and it strengthened understanding that the search for extraterrestrial life or intelligence isn't a sprint, but a marathon, requiring endurance, optimism, and readiness to continue even after many negative results. Because one day, maybe not with this object, not with the next one, but sometime in the future, if we continue searching thoroughly enough and long enough, we may find what changes everything. Several years passed since 3I Atlas disappeared beyond the range of human telescopes, dissolving into the infinite darkness of interstellar space. By the early 30s of the 21st century, the story about the comet that might have been something more became part of astronomical folklore. One of those stories told to students in lectures as an example of how science works with uncertainty. Young astronomers just starting their careers studied 3I Atlas data as part of courses on solar system small bodies, without experiencing the excitement that gripped their older colleagues during the actual events. For them, it was just another comet in catalogs, interesting for its interstellar origin, but no more mysterious than thousands of other objects orbiting the sun. But for those who lived through those months of waiting, who pointed telescopes hoping to see something unusual, memory preserved a special quality, a mixture of curiosity, hope, and ultimately calm acceptance of mystery. Avi Loeb continued his work on the Galileo Project, which by 2030 had become one of the leading research programs for searching for signs of extraterrestrial technology. The satellite network for near-Earth space monitoring was successfully deployed and expanded to 80 craft, creating virtually continuous sky coverage. In several years of system operation, 7 more interstellar objects were discovered, each with unique characteristics. None showed signs of artificial origin, but each added to our understanding of the diversity of conditions in the galaxy. Interstellar space population statistics were refined, planetary system formation models improved, and slowly, bit by bit, the picture of how our galactic neighborhood is arranged became increasingly detailed and accurate. Loeb continued publishing provocative papers and books, continued being a controversial figure, inspiring both admiration and criticism, but his persistence in searching for what others considered unlikely inspired a new generation of researchers not to fear asking bold questions. In 2032, the first Comet Interceptor-type mission launched, a spacecraft that took position at Lagrange point L2 of the Earth-Sun system and began awaiting detection of a suitable target. The mission was designed for 10 years of waiting, after which, if a suitable object isn't discovered, the craft would be sent to the best available target among long-period comets. This was a new paradigm in space exploration. Instead of planning a mission for a specific object known in advance, a flexible platform was created, ready to adapt to opportunities that nature would provide. The concept required patience and readiness to wait, possibly for years, but it maximized chances of studying a truly unique object when it appeared. In the space age, where missions were often planned decades ahead, such flexibility was revolutionary. Other methods of searching for extraterrestrial intelligence developed in parallel. The SETI program continued scanning the sky in radio range, expanding the search to optical and infrared signals. The James Webb Telescope and its successors studied exoplanet atmospheres, seeking biosignatures, chemical imbalances that could indicate life's presence. Several promising candidates were discovered, planets with unusual concentrations of oxygen and methane that in Earth conditions are produced by living organisms. But proving these signals have biological origin was extremely difficult, requiring exclusion of all possible geological and chemical processes that could create similar results. Exoplanet spectroscopy was at the edge of possible, even for the most powerful telescopes, and each observation required hundreds of hours of exposure to achieve sufficient signal-to-noise ratio. But research continued, slowly, patiently, with understanding that the answer might not come today, not tomorrow, but someday. By the mid-30s, the scientific community reached certain consensus regarding extraterrestrial life and intelligence search strategy. It should be multifaceted, using various methods simultaneously: radio and optical SETI for detecting technological signals, exoplanet study for seeking biosignatures, solar system monitoring for detecting anomalous objects that might be artifacts, searching for megastructures around distant stars like Dyson spheres, analysis of Earth's paleontological and geological record for possible signs of ancient visits. Each direction had low probability of success, but collectively, they covered a wide spectrum of possibilities. This was a diversification strategy, recognition that we don't know what form contact might take, if it happens at all, and must be ready for various scenarios. Funding such a multifaceted program required convincing governments and private investors of the long-term value of the search, even without guarantee of results. Interestingly, as searches continued decade after decade without positive result, public and scientific attitudes toward the question began changing. The Fermi paradox, the question of where everyone is if space is full of civilizations, began being perceived not as a paradox, but as a clue. Perhaps space's silence itself was important information. It could mean life is indeed extremely rare, that we may be alone or nearly alone in the observable part of the universe. Or it could mean technological civilizations are short-lived, that the path from intelligent life to interstellar travel or long-living civilization is strewn with difficulties that most don't overcome. Or, intriguingly, it could mean advanced civilizations intentionally hide their presence, following some cosmic ethic of non-interference, or simply because communication with less developed civilizations doesn't interest them. Each of these explanations had deep implications for understanding our place in space and our future as a species. There was also a more optimistic interpretation of silence. Perhaps we simply haven't searched long enough and thoroughly enough yet. Humanity has possessed technology for serious search for only about a century, since the mid-20th century, when the first radio telescopes appeared. This is an instant by cosmic standards. The galaxy is about 13 billion years old. If extraterrestrial civilizations exist but are separated by enormous distances in space and time, the probability that two of them would be close enough and sufficiently synchronized in their development for contact might be very low. We could search for another 1,000 years and find nothing, not because no one's there, but because space is so vast that even millions of civilizations could be invisible to each other at current technology levels. This perspective required humility and patience, qualities not always easy to cultivate in a culture oriented toward quick results and instant gratification. Reflecting on 3I Atlas years later, many participants in that story came to understand that the true value of the experience wasn't in confirming or refuting a specific hypothesis, but in the very process of investigation. Months of observations taught patience, precision, the importance of systematic approach. Discussions that flared around data interpretation showed how the scientific community works with disagreements, how consensus is reached through critical analysis and evidence accumulation. Public attention, though temporary, raised awareness about space exploration and inspired some young people to choose careers in science. Technological improvements implemented for monitoring the object continued serving other purposes, from planetary defense to asteroid cataloging. In this sense, even a failed prediction brought tangible benefit, demonstrating that the value of scientific investigation isn't always measured in confirmed hypotheses, but also in the process, infrastructure, and inspiration it generates. By the end of the 30s of the 21st century, 3i Atlas was somewhere far beyond Neptune's orbit, in that hazy zone where the sun's influence gradually fades and true interstellar space begins. Its velocity relative to the sun was about 30 kilometers per second, meaning in approximately 40,000 years, it would travel the distance of 1 light-year, the edge of the hypothetical Oort cloud, and enter truly interstellar space. From there, the journey would continue for hundreds of thousands or millions of years to the next star system, depending on its direction of motion and star density in that part of the galaxy. Throughout all this time, the object would drift in almost absolute darkness and cold, its surface temperature dropping to 3 Kelvin, the universe's background radiation. No activity, no changes, only infinite falling through the void, obeying inertia and weak gravitational fields of distant stars. There's a certain melancholy in contemplating the fate of such objects. They travel forever, never reaching a destination, because none exists. They're not alive, not intelligent, at least in any sense we can define, but there's something in their journey that evokes emotional resonance. Perhaps it's because their wandering resembles the human condition. We too travel through space and time, on a small planet revolving around an average star in a remote corner of an ordinary galaxy. We too seek meaning, connection, understanding our place in the grand scheme of things. And like 3i Atlas, we may never find definitive answers, may continue our journey in uncertainty. But in the journey itself, in the process of exploration and questioning, there's value and beauty. This is what makes us human, this insatiable thirst for knowledge, willingness to look at the dark sky and ask, what's there beyond our vision? Perhaps in centuries or millennia, if humanity survives and develops interstellar travel technology, one of our descendants will intercept 3i Atlas somewhere in deep space between stars. They'll have instruments we can only imagine, capable of analyzing the object with details unattainable by 21st century telescopes. They'll be able to answer questions we left unanswered: precise isotopic composition, mineralogy, internal structure, perhaps even determine which specific star system it came from. And when they read our records, archives of observations and discussions preserved in digital libraries, they'll see how we, with our limited means, tried to understand this mysterious object. Perhaps they'll smile at our naivety, or more likely, admire our persistence, that we did everything possible with what we had, never stopping asking questions, never ceasing the search. But even if this doesn't happen, if humanity doesn't reach the stars, the story of 3i Atlas will remain part of our legacy. It reminds us of that moment in history when we first began seriously seeking signs of other civilizations, when we transitioned from passive wonder to active exploration. It speaks of the courage to ask big questions, even knowing answers may not come in our lifetime. It teaches patience, the necessity to continue searching even after many disappointments. And it leaves us with a feeling of deep connection with space, understanding that we're part of something much larger than our small planet, our brief lives. Somewhere out there, in the cold darkness between stars, an ancient comet continues its silent journey, carrying with it secrets of another world. And we, here on Earth, continue looking at the sky, waiting, hoping, searching, knowing that one day, perhaps, space will answer our long, patient questioning. Until then, we continue observing, recording, analyzing, slowly expanding the boundaries of the known, one observation at a time, one hypothesis at a time, one interstellar wanderer at a time, in the eternal dance between curiosity and mystery, between the light of telescopes and the infinite darkness of space that guards its secrets as patiently as we strive to reveal them.